This meeting is being recorded.
Okay.
Okay.
So let me start. I
Great.
think that
Yeah, you can go ahead. So Paweł Traczyk will tell us about Burau braid representations for n equals 4. Take it away.
yes. So I think that the most important thing about my talk is to say happy birthday to Lou. And I think I will do it in the beginning of my talk in case I get so carried away by talking that I forget. I don't think I would forget something that important, but nobody can be sure. So now the next most important thing is that it is a common effort with Anzor Berize from Batumi, Georgia. So I think that there is no need to advertise the problem of faithfulness of Burau representation. The last unsolved case is for n equal to 4. And let me start by saying what conventions I will be using. So the conventions are here. The matrix is assigned to sigma 1, sigma 2, and sigma 3, the standard generators of the braid group are given here. You might have seen various versions. For example, nothing could happen if we replaced these matrices with very transpose matrices. That will be basically the same representation and surely with the same kernel. So the problem is whether or not the kernel is trivial. So let me introduce some further notations. Tau will mean just sigma 1, sigma 2, sigma 3. And gamma, sigma 3, sigma 2, sigma 1. Delta is standard notation for half twist. They are given here. And I think, can I do it? No, I need line, draw line. If you look at gamma and tau, you will see that they look more or less like backslash and slash signs. I will use this convention later in the talk. For now, it's not important. And let me produce here some obvious information. Like, for example, if you consider delta times tau, you can drag tau to the left, but at a price of changing it into gamma. Or the same if you drag tau through delta inverse, you just replace it with gamma. Also, somewhat less obvious thing, but also true, easy to check is that tau to the 4th power and gamma to the 4th power are both equal to delta square. Now, another important notation, what do I need now? Rectangle, are these two elements of the braid group before. One is very simple, that's beta, sigma 3 times sigma 1 inverse. The other a little more complicated, sigma 1 inverse times sigma 2 inverse times sigma 1, sigma 3 inverse, sigma 2, sigma 1. If you are familiar with homotopy approach to the braid group, you would probably see that they do not differ much. They are basically the same thing if you look at them appropriately. And now let me produce the information about the image of delta and delta square and delta to any power under the Burau representation. So here is the image of delta, and here is the image of delta square. It's very nice. It's just the identity matrix times the monomial t to the 4th power. Incidentally, yesterday I wanted to check whether it is a reasonable thing to give this talk, so I asked the artificial intelligence if the Burau representation is faithful for n equal to 4, and the artificial intelligence ChatGPT answered, of course not. Delta square is in the kernel. That's of course incorrect because this matrix is not the identity matrix, but it's not very far from it. It's the identity matrix times t to the 4th power. Now, here is a standard notation. The twist number for a braid is the sum of exponents for the generators. Now, there is one well-known fact that the group generated by these two elements is a free subgroup of rank 2, freely generated by these two elements in the Braid group. And another piece of information well known is that the kernel of the Burau representation for n equal to 4 is contained in this free subgroup, which means that if you look for an element, for a non-trivial element in the kernel, you just need to check elements in this subgroup, elements that are written as products of alpha and beta and alpha inverse and beta inverse, and you won't miss anything. And since the group is free, it's very easy to write all of them. That has been known for many years. I think that the first time it was announced, it was given in John Bierman's book, I think published in 1970 something, about braids. So it is known that if the Burau representation is faithful, then you can find a word in letter alpha, alpha inverse, beta, beta inverse, which is formally non-reducible and which has the property that when you substitute the images of alpha, alpha inverse, beta, beta inverse, then and you calculate the product, then the product is the unit metric. If something like that is possible, then the Burau representation is not faithful, and all non-trivial elements in the kernel are given in such a way. Okay, so we consider the problem of faithfulness of the Burau Braid representation for n equal to 4, and we know that it is equivalent to problem of whether certain two matrices, the images of alpha and beta, generate a free group. So let me calculate explicitly rho of alpha and rho of beta. Those are given here. If you look at these two matrices for a moment, you will see that these two matrices are very special. Like, for example, if you look at this one, you will see that obviously minus t is an eigenvalue, and minus t inverse is an eigenvalue. And if you calculate the determinant, it comes out to be 1. So it's obvious that 1 is also the eigenvalue. And you can also see that the standard vector 1, 0, 0 is an eigenvector for minus t, and 0, 0, 1 is an eigenvector for minus t inverse. Well, I have somewhere formula for an eigenvector for 1. It depends on t. So it's slightly different. Here it doesn't depend. And there is another important and interesting point. When you use this matrix, rho of A or capital A, as I denoted here, then when you apply this, when you apply the endomorphism defined by the matrix A to the vector V1, the vector for eigenvalue minus t for B, when it is sent to minus V3 to the opposite, to minus the vector, the standard vector for the eigenvalue minus t inverse. Of course, it means it doesn't toggle them. It's not true that phi of V3 would be minus V1. It's not that good, but phi A inverse of V3 surely is minus V1. And as I told you, these two elements in Braid group are really almost identical. They are very similar to one another. And you can guess that the matrix A, this one given here, the eigenvalues of this matrix are the same. It's minus t inverse, and 1. Well, it's not that visible as it was. Minus t is very visible. minus T inverse is less visible. But anyway, they are still these same eigenvectors. And if you choose properly eigenvectors for minus T and minus T inverse, you will have the similar property as before, that now phi b would send W1 to minus W3 and the other way around. So there is very nice geometrical setting in this case of n equal to 4. I would like one more remark about this. If you look at these eigenvectors, V1, V3 for A, no, V1, V3 for B, and W1, W3 for A, and you add D2 for eigenvalue 1 and W2 for eigenvalue 1, then you have 6 vectors. And they are as much linearly independent as possible. Of course, it's not possible for all 6 of them to be linearly independent, but if you choose any 3 of them, then they are linearly independent. So this is a sort of classical problem, a problem considered extensively in 1970s, whether 2 endomorphisms with such properties generate a free subgroup. And well, I will not go into details, but if you factorize the whole problem to the projective space, you can easily get the result saying that for a suitable number k, maybe not the matrices A and B, but the matrices A to the k power and B to the k power do generate a free subgroup of rank 2. In this case, it may be relatively easily proved that if you take k equal to 3, then these two matrices A cube, B cube do generate a free subgroup of rank 3 in the group of invertible matrices with coefficients in the ring of Laurent polynomial. So the next obvious question is that true for A square, B square, for the group generated by A square, B square? Now, surprisingly, it is much more difficult, and we do not have an answer to this yet, but I would like to show you some observations, some calculations, some experimental data concerning this problem. So, well, here is an obvious statement that certain 3 statements are equivalent. Let's forget it and go further. So we will consider this variant. We will consider the images of alpha square, alpha negative 2, beta square, beta negative 2. And we will consider the question whether these 2 matrices do generate a free group. And well, I could produce them, I could show how they look, but I will omit that, and I will try to go to some further simplification. Further simplification is that we can rewrite these special elements in the Braid group, alpha and beta, in a certain way using the tau, which was, what was it? Tau was sigma 3, sigma 2, sigma 1. So the fact is, and it was observed by Anzor Beridze's student David Tadze, So the observation is that actually alpha is equal to delta to negative 2 times tau 3 times delta inverse times tau 3. Alpha inverse is tau delta inverse tau, beta is delta inverse tau square, and beta inverse is tau square delta inverse. So we could replace alpha, alpha inverse, beta, and beta inverse with these matrices. And if you look at, oh no, just 2 lines above, you can replace it with that. And here, something that you could consider a disadvantage is that tau appears in certain powers, one of which has negative exponent. You have tau inverse here. But this may be easily, we can easily resign from that because we have already observed that tau square is equal to delta square, which implies that tau inverse is delta to negative 2 times tau cube. So we can replace alpha in this with the following version of alpha without negative powers of tau at a price of adding delta to negative 2. But delta to negative 2 is in the center of the braid group, which is very convenient because if you have a product of terms like this, you can just drag every occurrence of delta to negative 2 to the left or to the right or whatever you like. You can freely exchange it with everything else. So therefore, we will be restricting our attention to the products of such elements like here. We call them A inverse, B, and B inverse. They are almost identical with alpha inverse, beta, and beta inverse, with the exception that A small is slightly different from alpha. Now, so now in this setting, we are considering formally non-reducible words in alpha inverse, beta, and beta inverse. And when we replace alpha with this, of course, we got a different product. But the difference is insignificant because we have the control of it. The difference is that we have delta to negative 2 appearing several times. And if we just have the word written in these terms, alpha, A inverse, B inverse, we can easily recover that because, as you may easily see, when you write those terms, alpha and beta, let's go back to them. When you look at alpha and beta as originally defined, then they have a nice property that the sum of exponents of the standard generators is equal to 0. Here is -1, -1, -1, 1, 1, 1, and here is 1 and -1. So when you have a word in this alpha and beta generators and you want to recover the word in A and B generators and you want to recover this notation for alpha and beta, you can do it very easily just by adjusting, by multiplying by delta to a suitable power that will assure that the sum of exponents of the standard generators would become 0. Okay, so now I am tempted to use a somewhat frivolous notation because I need to write delta inverse several times, so I invert the letter delta with nabla. It's frivolous because nabla is well established as a letter used for something else. So it is still true that gamma times delta is equal to delta, gamma times nabla is equal to nabla times tau, and tau times delta is equal to tau times nabla is equal to nabla times gamma. Also, we have this definitions for, I'm just rewriting this here so that it will be visible for the calculations. So you have this that was given a few lines above, but on the previous page. And we still have what was mentioned in the beginning, that tau to the fourth power and gamma to the fourth power are both equal to delta square. What is really important is that tau to the sixth power is equal to delta square tau square, and gamma to the sixth power is equal to delta square gamma square. Now let me give you an example. Let's consider a word a to the fourth power. So we repeat this term 4 times. And when you use all the information that you can get from this, you can see that it is equal to nabla to the fourth power, delta to the sixth power, and then tau cube, gamma square, tau square, gamma square, tau cube. You may be surprised that I used nabla to the fourth power times delta to the sixth power because I could cancel. But the reason for that was to stress that this nabla to this delta to the sixth power is here because of these 3 products. This is tau to the sixth power, and tau to the sixth power is delta square tau square. So I moved delta square to the left and left it here without cancelling with nabla to the fourth power. Let me show you some further examples. So I have a to negative 2, b to the fourth power, a to negative 2. This is equal to that sort of product. As you see, I'm exploiting here the terms that are in the alpha square b square subgroup. So the exponents here are all even. Now, I marked some parts of that with red. Now, what's the meaning of this? Here you have b to the fourth power. And as you see, you have gamma square tau square gamma square 3 times. And then you have tau to some odd power and tau to another odd power to the left of this and to the right of this. And this is what always happens when you take any product in which alpha and beta appear with even exponents. When you will have a sequence where when you simplify it in this way, you will have an alternating sequence of tau letters and gamma letters. Okay, but that's one entity. Gamma square is allowed. I'm not saying that after gamma you need to have tau. Tau square is allowed, and tau cube is allowed, and single tau is allowed. Now, if you look at it properly, you will see that gamma, then that tau to an odd exponent will only appear when a part of the original product meets a b part. So here you have 2 places like that. Let's erase this. You have a single tau here and a single tau cube here. That's because here what remains of this and that meet here, they meet here, and at this place you see the result of these 2 being next to one another. Now, I said something that is not exactly true, because you also have a single tau at the beginning and a single tau at the end. But that's the only exception. You may have tau to the odd power at the end, or you may have tau to the odd power at the beginning. Otherwise, they only appear as marking the boundary between A and B letters. So I have a number of examples like that. I will not go through the calculation. It's pretty obvious, I think, that if you have something like that, then you need to move nabla to the left. Whenever you meet nabla to the left, you replace tau with gamma. And when you move another instance of nabla to the left, this gamma becomes tau again. And when you do it for the third time, it is again nabla. So you can see immediately that in this case you have 1, 2, 3, 4, 5, 6, 7, 8 nablas, which means that tau will finally remain as tau. Now, if you have tau square here, but this time you only move 7 instances of nabla to the left of it, so that becomes gamma square rather than tau square, and so on. That's the reason for which they do appear in an alternating manner. So let's forget these calculations. How about my time? Oh, it's almost the end. So let's go further. Let's just say that a braid that is written as an irreducible word in letters a square, a negative 2, b square, b negative 2, assuming that it ends with a square or a negative 2, it may be rewritten in letters nabla, tau, and gamma in such a way that some power of nabla appears first, then you have a sequence of symbols beginning and ending with gamma square, and it alternates gamma square and I wanted to say something else. If you have a sequence of gamma squares and tau squares like here, without gamma or tau to a negative power, then it begins with gamma and ends with gamma, always. Here is another sequence like that. Here is a sequence of length 1, and it also begins with gamma and ends with gamma. Now, between them, you may have tau or tau cube, and they just serve as markers for ending one of such sequences and starting the next one. Here, you had B4. If you have B to the 6th power, you would have again one more tau square delta tau square gamma square. You have the sequence would be of length 5. Okay, so let's forget this. And one might ask a question whether from a notation like this you can recover the original A and B notation. And the answer is that, well, it's almost true. It's not really true that every sequence like that comes from a sequence like that, even if the exponents are chosen well, but it's almost true. And if it is true, it's easy to do. But maybe I will make just a small remark about how it works. So if in a sequence like that, you see, shall we say, you see tau cube, you know that that's a place where A meets B. You have A to some power here and B to some power here. And the nice thing is that if it is tau cube, then the A and B letters that may meet at this point are either AB or BA inverse, or A inverse B inverse, or B inverse A. If it is single tau, then it's the other way around. It's BA or A inverse B, or B inverse A inverse, or A B inverse, which means that you can easily recover the word in A and B letters if you want, if you know how to start. And you know how to start if you know the last term. Okay, so now I used a lot of time, but I want to tell you to show some calculations. So now I want to go to my terminal, and I'm not sure if you can. Can you see my terminal?
Yes, we can see your terminal.
Okay, if you can see my terminal, that's good. Let me calculate 3 specific examples. Oh no, not this way. I must. Okay, so I will calculate 3 specific examples. For a moment, I'm doing it step by step, but let's press Q to go right to the end. So what is given here? What is given here is the image of this particular word. As I said some time ago in the beginning, for calculations, for giving input from the screen, it is convenient to use slash and backslash rather than sigma and gamma. Obviously, slash is for sigma, and backslash is for gamma, which is probably less obvious. So this is sigma cube, gamma square, sigma, gamma square, sigma, gamma square, sigma, gamma square, sigma, gamma square, and sigma, gamma square. That's the image. Now, what does it mean that it's the image? That's a matrix, a 3x3 matrix, and the entries of the matrix are polynomials, and they are too large to put them on the screen, so they are cut at some point. So at position 1, 1 in the matrix, you have -2 times t to the power 14 plus 6 times t to the power 15 minus 5 times t to the power 16, and so on. Here you have more of them. It's the same. This and this are the same, only this is cut at a later point. So in the brackets, you have an indication of what is the lowest degree term. The reason for which I'm showing you this example is that if you try calculating examples, you might be under impression, at least initially, that the polynomials that are coefficients, that are entries of the matrix, that they are always monic. They are not, as you can see. You have a leading coefficient -2 here and -2 here, and so on. So that's one example. Now let's go to another one. Let's go straight to the end by pressing Q. Now this is more spectacular example because you have the leading coefficient at the lowest degree, end. You have -18, and here -18, and here -9, and so on. But let me show you this in a better way. I will back step to this position. Now let's look at this. This is actually the same word that I used in the first example, and the whole thing is the cube of this word. So you take this and you calculate the image of the cube of this term. Now you can see immediately that if you calculate this, you must raise this matrix to the 3rd power. And when you know how to multiply matrices, when you multiply the first row by the first column, you will have -2 times -2. And then you will have -1 times -2, which altogether makes 6. And the coefficient will be 28, because they multiply nicely. This term, 6 times t to 26, will not cancel with anything else in the product. Now I go to this position. I must backstep because I waited for 3 slashes to know where the second term stops. And as I told you, it's 6 times t to power 28. And when I go right to the end, the same story happens again. They multiply nicely, and you have this special, really non-monic polynomials. Now let's go to another example. That's what is it good for? Let's see. Something very special here. It starts with s cube tau square, s cube tau square, tau s cube tau square, and so on. And it's against non-monic, but it has a very special property, which is that in the columns, here is the whole matrix, and here you have just the columns. So in the columns, the leading terms are of the same lowest degree. In the first column, the lowest degree is 39. In the second column, the lowest degree is 40. And in the third column, the lowest degree is 42, as you can see here. Now, let's go. Maybe I will leave this, but I will go to another terminal. Let's look at this. In this terminal, I have a lot of experimental data showing certain names of files. The files record the lowest degree terms, the degrees of the lowest degree terms for words beginning with something. I record 1, 2, 3, 4, 5, 6, 7, 8, 9 initial groups starting from the left. Now, actually, the listing lists the recorded results according to the size. So, as you see, if I go up, there are some results that are very unusual, like 12 kilobytes, and here you have 400 or something, 448. So how to read this data? This indicates that in the second column, the first term has smallest degree exponent bigger by 1 than the second term, and the third term in the second column is smaller by 2 than the middle term. And that's very usual situation, it's a very typical situation. And to end, let me just show you the same data arranged nicely in a spreadsheet. I instructed the spreadsheet to start listing by showing examples beginning with b cubed. Oh, now b is for backslash, s is for slash. Then single s, then obviously double backslash because that's what always happens. Then triple slash and double backslash and double slash and double backslash. Oh no, now it's just anything. So I just insisted on the single slash at the second position and triple slash at the fourth position and double slash at the sixth position. And now you have information about the lowest degree terms in the second column. And you can see that, let me show you. So let's see that at the last position in the second column, you have only -1 or 0. So the exponent is smaller by 1 than the exponent for the middle term, or it is the same. And in the first position in the second column, it is always bigger by 2 than in the second position. In the second position, it's always 0 because that's what we compare it to. We compare to the term in the second position. Of course, I'm not saying that in the second position, they all begin with t to the 0th power. They begin with many different things, but I just normalize putting them all to 0 by adding the actual lowest degree exponent. Okay, so in the previous example, I was showing to you an example of a friendly multiplication. In this case, multiplication was very friendly because low degree terms met low degree terms when we multiplied, and there was, oh no, too far. Okay, never mind. Now I destroyed it probably, but I am out of time. So I just want to say the following. In many cases, the matrices are multiplied in a very nice way in which you can uniquely recognize what the lowest degree term will be. And the observation obtained by analyzing millions and probably billions of examples show that the lowest degree terms are too low for the representation being unfaithful. That is, they are lower than we would expect if we had something in the kernel. If we had something in the kernel, we would expect that, taking into account that we put some delta square to some power to the left, we would expect what would we expect? We would expect a diagonal matrix looking like that. We would know what exponent we should expect as the leading term. And what really happens is that they are always smaller than that. Okay, so we hope more or less that using some zipper technique, that is cutting the word in a clever way into several segments, we would obtain nice multiplication, giving the lowest degree term as being too low for the image of the word being of that kind as given here. Okay, so that's it. Oh, there is one more important thing. I wish to say happy birthday to Lou. I'm not sure if I already told that because I'm too excited to remember. So just in case, I repeat, happy birthday to Lou. Okay, thank you for your attention. Now. Grzesiu, chodź teraz tutaj. Może będą jakieś pytania.
If you have any questions for our speaker, feel free to unmute and say them out loud. And if you're more comfortable, you're also welcome to put them in the chat.